Okay, let's get started. So we are in topic 5 and learning about multivariate inference about a mean vector. Last time I reviewed the topic 4 stuff that talked about sampling distributions and likelihoods and maximum likelihood estimation. Just to underscore that and to tie in with what we're doing in topic 5, let's think about, as a review, a univariate example. Suppose we have a univariate random sample. So these are all x1 through xn are single numbers, not multivariate. They're independent and identically distributed, let's say from the normal distribution with a mean and a standard deviation. So our estimate, the way that we would take these observed in variables and turn them into an estimate of the mean, is with the sample average, x bar. That also happens to be the maximum likelihood estimator. So statistical inference is not just about estimating a parameter value. X bar is an estimate. If we had to pick a single value as our guess, our best guess at the value of mu, we would pick x bar. But we're almost certain that x bar does not equal mu. Mu is a population parameter. X bar is a sample statistic that we're using to estimate that parameter. But it's just an estimate. And because it was computed from randomly obtained data, x bar, an estimate or statistic, is random. And for inference, confidence interval or p-value, we need the sampling distribution of this statistic. It turns out in the univariate case, if our data are normal, as I've written here, the sampling distribution of x bar is also normal. It has a mean mu, and it has a standard deviation equal to sigma over the square root of n. So Stat 101 stuff, whenever you have normally distributed data, inference follows easily because we know what the sampling distribution of x bar is. In practice, we don't know what sigma is, so we estimate it with a sample standard deviation like S, in which case, instead of x bar being normal, we refer to a t distribution. But it all starts with this result here. With data, we have an estimate, which is a statistic, and a statistic is random, so it has a distribution. Sampling distribution is the special term for the distribution of a statistic. And before we can get p-values and confidence intervals, we need to know or be able to approximate what the sampling distribution of our statistic is. So going back to topic 5, our goal is to do inference, p-values and confidence intervals or regions for mean vector, starting out with just a single mean vector. And then we'll consider comparison of 2 mean vectors, or eventually comparison of 3 or more mean vectors. But it's the same idea. We need sampling distributions. So here we started last time as a review of the univariate case and motivating the t-test, the usual one sample t-test. We construct a statistic. So we said in the whiteboard just now that x bar is a statistic. It is a statistic. Anything that you compute from data is a statistic. For the purposes of hypothesis testing, we typically want a specialized statistic that we refer to as a test statistic. So a test statistic is just a statistic that's specifically designed to quantify how different our observed data are from what we expected them to look like under the null hypothesis. The t-statistic, test statistic, for example, is a standardized version of x bar. As a reminder, if a random variable is normal with mean mu and standard deviation sigma, then what's the distribution of this quantity? It's still normal because I'm using the actual standard deviation sigma. If I estimated sigma with s, then we would talk about t. But using the known parameters, mu and sigma, if I take x and subtract its mean, it's still normal. That's like taking a distribution centered at mu and shifting it to be centered at 0. Subtracting a number doesn't affect the distribution. And then dividing by sigma, similarly, does not affect the distribution. It affects the scale, how spread out it is, but it doesn't affect the bell-shaped nature of it. Subtracting mu and then dividing by sigma, we still have a normal random variable. Subtracting mu means that the expected value, the average, is going to be 0 because we have shifted everything by mu. And dividing by sigma makes the variance and standard deviation equal to 1. So that's a standardized version of x. Standardized version of x. We've taken an arbitrary normal random variable and we've transformed it to have the standard normal, which is the normal with mean 0, standard deviation 1. This looks a lot like what I just wrote down. It's x bar minus a constant, a mean, divided by a standard deviation. So based on what we just saw, a couple of things. One, the sampling distribution of x bar is normal. Its mean is mu, and its standard deviation is sigma over the square root of n. So if I were to do x bar minus mu divided by sigma over the square root of n, what would be the distribution of that? Hi. Yeah.
Sorry to interrupt.
Yeah, no problem. I'll let you know if I see it. The distribution of this would be normal with what mean?
0.
And what standard deviation? 1. For the same reason as what I wrote down a moment ago. X bar is an arbitrary normal random variable. It happens to have a mean mu and a standard deviation sigma over the square root of n. So if you take x bar, subtract its mean, divide by its standard deviation, you get back standard normal. That looks even closer to this right here. So this test statistic, the t statistic, under what scenario, under what condition will that be approximately normal 0, 1? What is a condition for that quantity to be approximately normal 0, 1? What about the mean? Which mean did we use to subtract off? The null hypothesis mean. We don't know that that's the right mean. We're playing pretend and saying, suppose that the null hypothesis is true. So if mu0 is the right mean, then we have appropriately scaled the x bar, and we should have a result like this one. So this test statistic is constructed in such a way that when the null hypothesis is true, this should be like a standard normal random variable. For technical reasons, it's not quite standard normal because instead of dividing by the actual standard deviation that involves sigma, we don't know what sigma is. So in practice, we have to estimate sigma. And the penalty for doing that is that we no longer have standard normal. We have a slightly modified version of the standard normal, a t distribution. Just FYI, if this is the standard normal, then this is the t with n minus 1 degrees of freedom. Normal distribution has two parameters, the mean and the standard deviation. A t distribution has just one parameter, and it's the number of degrees of freedom. It's the little subscript that we put next to the t. So depending on what the value of n is, you'll see a slightly different red curve. And as you increase the sample size, as you increase n, it turns out that the red curve settles down, converges to the standard normal. So if we looked at that t curve, t distribution, and we dialed up the sample size to really, really big, then the difference between t and standard normal becomes negligible. But generally, the t distribution is a lot like the standard normal, except we have more uncertainty. It's spread out more. The tails are fatter. But that's the idea behind the t-test. You have data. You have a question you want to answer confidently. So you formulate it into a null and an alternative hypothesis. Step one from there is to construct a test statistic, a number that will quantify the strength of evidence in our observed data against the null hypothesis. And a sensible way to do that is to standardize x bar as if the null hypothesis were true. So if the null hypothesis is true, then this that we observe should have come from the expected reference distribution. If we then draw, say, the t with n minus 1 degrees of freedom, and here's our test statistic. It's way over there on the right. What we're doing is we're assuming the null is true. And then we're saying, okay, assuming the null is true, the red curve should be controlling the values that I see. But maybe I saw that green t, which looks very unlikely to have come from the red curve. Then that's my quantitative way of saying the null is probably not true. And to be specific, what we would do is compute what's called a p-value, which is the area under the curve that corresponds to as or more extreme as our observed test statistic value. And if that's small, like it is here, because the area under the curve way over there in the tail is very small, the probability function is close to 0, we would have a very small p-value. And a very small p-value, roughly speaking, is indication that your null hypothesis is not right. If the null hypothesis were true, I would expect to see t-statistics that are in this region where there's lots of probability. So when I see something way out in the tails, that's an inferential indicator that I probably made the wrong assumption about the null hypothesis. Okay, so I'll stop talking about the basics of hypothesis testing, and let's move from univariate t-test to multivariate t-test. This is the usual t-statistic. All it is a standardized version of x bar. When we have normally distributed data, x bar is approximately normal itself. So this is approximately standard normal. Because of the S, we have to penalize ourselves, put more uncertainty, and that means a t. Notice that if you square the t-statistic, you get this thing. Although I have a typo, the numerator should have a squared exponent. All that is the squared t-statistic. And then notice that I can write that in a little bit of a different way as down at the bottom. This quantity is the exact same thing as the squared t-statistic. And for the purposes of doing inference, like computing a p-value, I could work with this test statistic, the usual t-statistic, or I could work with this one. It'll be equivalent as long as I compute and use the appropriate sampling distributions. The sampling distribution of this one under the null is t. The sampling distribution of this one under the null is whatever t squared is. Does anybody know what the distribution of a t squared is? Okay. So we'll see that in a second. So I am going to spend a fair amount of time on these initial slides because statistical inference is very critical to statistical practice. And much of what we're going to see in the next couple of weeks is statistical inference. Doing inference on a mean vector, inference on a difference of mean vectors, inference on a difference of 3 or more vectors. So I want you to really understand what the philosophy of hypothesis testing is and what a confidence interval, confidence region is. So slide 5. What we're doing with hypothesis testing is we are trying to choose between two possibilities. The null possibility or hypothesis is that the mean is equal to some selected value. And the alternative or research hypothesis is that that's not the case. So we want to look at our data and ask which of those two possibilities do the data support most. And remember that hypothesis testing proceeds by assume the null hypothesis is true and ask of the data, is there enough evidence to reject that assumption? Just like in the legal setting, we assume the accused is innocent and it's on the burden of the prosecutor to change our mind. Okay, so then the way that we do the actual decision is related to this picture. We have data that we observed. We compute x bar, we compute s. We put those together into a t-statistic, a test statistic. And then we compute or approximate the sampling distribution of that test statistic under the null hypothesis. And then we ask, where is my test statistic relative to that sampling distribution? And I'm going to reject or change my mind. I'm going to reject the null hypothesis or change my mind if my statistic is sufficiently far in the tails of that sampling distribution. So here we have to decide how far is sufficiently far. That t statistic is way out in the tails, but suppose it was like right there. That's still an unlikely location, an unlikely value to see, but it's much less unlikely than this one. So what we do is we pick a probability value that is how unlikely does this test statistic have to be before we will reject the null hypothesis. That's sometimes referred to as the significance level or alpha. So when we do hypothesis testing, we say we're doing a hypothesis test at significance level alpha equal ... Common choices are 0.05, 0.01. Suppose we said we're going to do a hypothesis test at significance level alpha equal 0.05. What that means is I'm going to reject the null hypothesis if the area to that further at or further than my observed statistic is less than 0.05. So what that, ow, I slept on my neck wrong somehow. I got like pain. So what that means is if the null hypothesis were true, we'd see in less than 5% of cases a test statistic like ours just by chance. Even in this picture, it's possible to see that t. There is probability over there, it's just unlikely. So we have to decide how unlikely is sufficiently unlikely for us to reject the null. And we do that through the choice of alpha.
Is this a one-tailed t-test?
This that we're describing is on this slide, we're talking about a two-sided alternative. The way that I'm kind of sketching things in this picture is more like a one-sided alternative. So I'm trying to be careful in my language. The p-value is the area under the curve that is as or more extreme as our observed statistic. What as or more extreme means depends on what is the form of our alternative hypothesis. Is it, yeah, I'll leave it at that. I don't want to burden you with too much talking. So then mechanistically, the way that we make a decision is we're going to reject the null hypothesis if our statistic is far enough out in the sampling distribution that there's less than alpha % probability out there. An alternative way to say that is that we will not reject the null hypothesis. We'll stick with our original assumption if our statistic is close enough to the mean. It's not past the threshold that corresponds to alpha. So let me jump forward a little bit and try to tie in with confidence intervals. All that I was talking about is hypothesis testing stuff. Statistical inference, two sides of the coin are hypothesis tests and confidence intervals. A hypothesis test is just making a formal decision with a stated level of confidence. A confidence interval is let's estimate the value of something with a stated level of confidence. And they're tied closely to each other. In particular, this plan to reject the null if our statistic is sufficiently far in the tails is equivalent to computing what's called a confidence interval and checking whether the hypothesized value of the parameter is inside that confidence interval. So these two statements are equivalent. Let me say something about confidence intervals. We observe data. This is univariate case. Suppose they're normal. Based on our data, we compute sample statistics, sample mean, sample standard deviation, and a 1 minus, okay, so let's say x bar s, and let's say we're going to do inference on mu at significance level alpha. We could either do this with a hypothesis test or with a confidence interval. Stats 101 would tell you that a 1 minus alpha times 100% confidence interval for mu is sample mean plus or minus a what's called critical value, which is basically a boundary. How far out in the null sampling distribution do you have to go before you're in that alpha range? How far out is far enough to reject the null? And we represent that, depending on the specifics of the setting, with a name, typically a letter that indicates the type of distribution, in this case T. I need the number of degrees of freedom. And then either in parentheses or in subscript, we indicate how far out we went. So let me write this down, and then I'll comment on it. A 1 minus alpha times 100% confidence interval for mu is x bar plus or minus critical value times standard deviation of x bar. This is of the form estimate plus or minus a cutoff times the standard deviation of our estimate. Remember when I last time talked about test statistics, I said one common form of a test statistic is estimate minus what you think the parameter value is under the null hypothesis divided by the SD of the estimate. Just in a similar way, confidence intervals often have a common format of this form: estimate plus or minus a cutoff or a critical value that dictates how far out is far enough times the SD of the estimate. So that would be called a confidence interval for mu. We could make that, for example, a 95% confidence interval for mu. And then let me draw you a picture that speaks to the interpretation of a confidence interval. Imagine that that's the true value of mu. Whatever the context, we're observing some normally distributed phenomenon, and in the population there's an average. That's the average. Maybe it's 4.08. Because we can't assay the entire population, we went out and got a sample of size n, a random sample from this population. And on the basis of that sample, we constructed a 95% confidence interval. So suppose that this green line segment from the left point to the right point is the result of going out and getting 100 draws from the population and doing x bar plus or minus critical value times s over the square root of n. let's say it's a 95% confidence interval. In the real world, we spent money, time, resources collecting these 100 observations, writing down the data, doing the data analysis and everything. And we wound up with a single confidence interval. What I'm going to go publish or submit for publication is this green interval. My estimate for where the mean whatever is in the population goes from the lower endpoint to the right endpoint. And I'm 95% confident in that. So what does that really mean when I report that? What people want it to mean is that the probability mu is in my interval is 0.95. That's not exactly what we get to say, though. So the way we think about confidence intervals is, there's my sample of size 100. Now suppose somebody else goes out and gets a different sample of size 100. And for their sample, which will differ from mine just by chance, they compute, again, a 95% confidence interval. It looks different from mine because their data is different from mine, just by chance. So imagine that process happens lots of times. Suppose we did this thousands of times. We're repeating the process of collecting data and constructing a 95% confidence interval. The way we interpret 95% confidence interval is 95% of all intervals constructed in this way can be expected to contain the truth, the target parameter. And the flip side of that is 5% of the time, when you do this routine, pay the money and the time, go collect your 100 observations, measure them, run it through the algorithm to compute one of these things, all you have to show for it is your one interval. And you have no way of knowing whether your interval is a red one or a green one. All you can say with statistical inference is you used a technique or a method that works 95% of the time. That's sufficient to drive science and decision making, but it's unavoidably kind of subjective, because ultimately you can't guarantee whether your interval contains the truth. So imagine what that means if we zoom in on one of these things, like that red one right there. That's the result of somebody going out and collecting 100 individuals from this population. There's nothing wrong with the individuals or the way they were collected. There's nothing wrong with the data that they collected on those people. And there's nothing wrong with their calculations to construct that interval. Just by chance, because of the way probability and inference works, just by chance they got unlucky, and for their sample, the interval was off. They estimated that the mean was from here to here, and the actuality is that the mean's not in between those two numbers. So the purpose of this slide is to say a couple of things. In the univariate case, in order to test and do inference on a single mean, we can either do a hypothesis test, or equivalently, we can construct a confidence interval. So if I do a hypothesis test, I'm going to reject the null hypothesis if my statistic is far enough out that there's less than alpha probability over there. If I do a confidence interval, what I ask is the null hypothesized parameter value contained in my confidence interval? Yes or no? And if the answer is no, I reject the null hypothesis. And those two things, those two approaches will agree. If the t-statistic is too extreme, then you know that mu0 is not in your confidence interval, and vice versa. One more small detail before we move forward. Yeah, I already said, but I wanted to emphasize when we put the test statistic that we observe up against the hypothesized sampling distribution, and we ask, is the statistic far enough out? Is it extreme enough? The way we will actually quantify that typically is by computing what's called the p-value. P-value is the area under the sampling distribution that's more extreme than what we actually saw. So that's like the probability of seeing a statistic like we saw, or more extreme, if the null is true. And what we can do with that p-value is ask, is that less than alpha? If alpha is the significance level we want to use, I'm comfortable making a decision with a 95% confidence, then I'm going to reject the null if my p-value is less than 0.05. So the equivalence is, to do inference on mu, you could compute a p-value and ask if it's less than alpha. If so, reject the null. That's equivalent to computing a 95% confidence interval or a confidence interval and asking whether mu0 is contained in there. And if not, you reject the null. In either case, you have the same strength of evidence.
What is the significance of dividing the alpha by 2 in that form?
So the division by 2 has to do with the fact that of the form of the alternative hypothesis. So this presentation here on this slide, we have things set up so that there's a null, that mu is equal to mu0, and the alternative is that mu is not equal to mu0. Mu can not be equal to mu0 in two different ways. It can be bigger than it, or it can be less than it. So that's called a two-sided alternative hypothesis. When it's not equal to, it can either be in this direction or that direction. So the alpha over 2 is there because essentially in the sampling distribution, we want to reject the null if our test statistic is too far out in either direction. It's way bigger than 0 or it's way smaller than 0. In order to make the total area of rejection equal to alpha, what we do is we go out to where there's alpha over 2 to the right and there's alpha over 2 to the left. So this Tn minus 1 alpha over 2 is going in either direction. Let me draw a picture. Suppose this is the t with n minus 1 degrees of freedom. Here is n minus 1, let's say 0.025. And here, the t distribution is centered at 0. Over here is the negative of that quantity, because it's a symmetric distribution. The area to the right of this is 0.025. And the area to the left of that is 0.025. So the total area that's being marked off is 0.05. If I wanted to do a test at significance level alpha equal 0.05, then if I wanted to allow for the statistic to be either big positive or big negative, this is a sensible way to do it. In this setup, if my test statistic is over here, I will reject. But also, if it's over there, I will reject. So the idea, the reason that we have the alpha over 2 thing is because I'm trying to split up the total alpha to both sides to allow for either type of deviation from the null hypothesis. I would recommend that if there's any uncertainty there, go get a basic intro stats book and review the material on null and alternative hypotheses and p-values. It should walk through that for you. But that's where this comes from, is the basic hypothesis testing theory.
So based on the data, we decide whether to go for a one-tailed test or a two-tailed test.
The choice of whether you want a one-tailed or a two-tailed alternative is usually answered by the scientific context. What is the question you want to ask? Suppose we're studying the pH level of a pond, and is there an acid rain problem or something? There's a natural direction in that case. Is there an acid rain problem? That would look like the average pH in the lake is less than some threshold, 5 or something. So my scientific question would be formulated as a null and an alternative. The null would be that there's not an acid rain problem. And the way we would formulate that is we would pick the actual boundary value. So I would actually say the null is that the mean is equal to 5. But my alternative would be one-sided because I specifically care about is it less than. If it's a drug and we're asking like what is the impact of this drug on blood pressure or something. You don't want to increase somebody's blood pressure, but you don't want to lower it too much either. So we might ask, does this drug have an effect on blood pressure? Yes or no? The null hypothesis is no. The alternative is yes, and we care about either direction. So the choice of form for the alternative, usually you answer that, you pick that before you even look at data. Okay, so now we're ready for Hotelling's t-squared. And the easiest way to go from the previous slide to this slide is actually to start with slide 4. So the bottom of slide 4, I mentioned this a moment ago, the bottom of slide 4 is just another way of writing t statistic squared. This is just a different way of writing that squared. And the reason I wrote it this way is because when we go to multivariate, so notice the form of it. It's a constant sample size times the difference between the mean and the null mean times the inverse of the variance times the difference between the means again. So in a vector sense, natural way to make that the vector style is like this. I have n times a difference between the means, but now they're vectors. Instead of dividing by a variance, the matrix analog is to multiply by the inverse of the covariance matrix. And then here's the difference again. This then is a multivariate generalization of a t statistic. If the null hypothesis is not true, we expect this thing to be big, extreme. Because it's actually like a squared t statistic, we actually expect it to be big positive. This will be non-negative. Evidence against the null will look like big positive t squared statistics. From here, the math will look a little different, a little more complicated, but the concepts are exactly the same. We're going to compute p-values, and we're going to construct confidence regions. We're going to reject the null if the p-value is less than alpha. And equivalently, we're going to reject the null if the null hypothesized mean is not contained in our confidence region. The only question then is, how do we get a p-value? How do we get a confidence region in this multivariate setting? I told you last time, or the time before, that going from data to p-value or confidence interval is all about sampling distributions. In particular, I need to know what's the sampling distribution of my statistic. So here's the math. the sampling distribution of the t-squared statistic, which is named after a famous statistician named Hotelling. The distribution of t-squared, when the null hypothesis is true, can be analytically derived. So it's a couple of constants times an f distribution. Somebody correctly said earlier, what's the square of a t? It's f. So not surprising that our Hotelling's t-squared statistic refers to an f. This is the f distribution. F distributions have two different degrees of freedom. The t distribution just has 1 degree of freedom. F has 2. So you have to specify p and n minus p. What's p? Number of variables, right? Number of columns in the spreadsheet, number of numeric variables. So to do a test, a hypothesis test for a multivariate mean, if my null is that the multivariate mean equals a vector mu0, and I want to do a two-sided alternative versus that mu is not equal to mu0, and I want to test at significance level alpha, then we will reject the null hypothesis if our test statistic is extreme enough, is big enough. Big enough is answered like we did in the t case. This is called a critical value. So up here, this is just fp n minus p. Down here, it's fp n minus p parentheses alpha. When we have the parentheses alpha, what I mean by that is these types of quantities. So the f with p and n minus p degrees of freedom, f p n minus p of alpha is the number that puts alpha to the right. T-squared statistics will tend to be big positive. If the null is false, we'll see big positive test statistics. So how big positive does it need to be for me to say it's big enough and reject the null? That's where this critical value comes in. This is the number that separates out the most extreme alpha percent possible values. So if our test statistic is in that red region, we confidently reject the null. We could skip this slide. If you're interested in the mathematical theory, the distribution theory, there's some connections between the univariate t and the multivariate t. The t could be written, if we squared it, as normal times chi-square inverted times normal again. T squared, similarly, multivariate normal, multivariate version of chi-square, which is called Wishart, inverted, multivariate normal. That is the source of the mathematical relation that gives rise to that actual F distribution. If you take something like stat 414, 415, or 610, 611, that's the type of stuff, mathematical statistics, that you would learn. Okay, we're out of time, but next time we'll go to some data and use our new toys. So we'll do a test for a multivariate mean, and then eventually we'll start doing confidence regions. All right, see you Friday.